Okay, let's go. Good afternoon, everybody. Thank you so much for having me again today. We will try to move forward with our knowledge. Before I proceed, I'll do a little recap of what we did the last time. And then we'll define vectors, look at atomic vectors, lists, and then do the exercise I told you about. We'll start this with a quote by a man called John Chambers. John Chambers is considered to be the father of R. The father of R, not the inventor. R was invented by two professors, Ross Ihaka and Robert Gentleman. I think University of Auckland, New Zealand. They're the ones that invented R. But John Chambers is the father in that John Chambers invented a language called S. Many years ago in Bell Labs. If you know of Bell Labs is currently known as AT&T, the U.S. telecoms giant. He was a staff of Bell Labs then, and he came up with a language called S. S is a computing language. S, just S for school. S is a language purely for statistical analysis, owned by that company for which he was working. Now R was based on S initially when it was initially invented. Okay, as an open source version, an open source equivalent of S, using the fundamentals of S. So that's who John Chambers is. The man is in the 70s right now, still very active, in the R process. Still very active in the 70s. So he said that to understand computations in R, two slogans are very helpful. Everything that exists is an object, and everything that happens is a function call. If you remember last time we met here, I told you that every action is carried out by a function in R. Anything that is an action, a computation, any change that you make in your system that you carry out through R is done with a function. And that's what this means. And everything that exists. Last time we met, I told you about variables. So everything that exists is an object. Even functions that just their existence, they are objects. All right. So it's a good thing to bear in mind. As one grows in knowledge of R, you find out that this is really it helps you to grasp how to manipulate and program in R. Now, before I also continue, there are two things also about R that I wanted to let you know, and this is also the beauty about R. There are two kinds of people that work with R. We have R users, and we have R programmers. You don't need to be a programmer to use R. Not at all. So it's a good language to share with people who don't have any computing background and who probably have no plan to ever go into computing per se. But you can use it to work, as a tool to carry out data management, data analysis, and so many other things. All right. Now, what we did last time, we did some computations in the R console, typed a few things into the console, we saw the results, the outputs. We tried to create some variables. What's a variable? Please let me ask you. What's a variable? What's a variable? Okay. It says okay. It says value changes. It's a memory location. All right. Ernest, are you busy doing something else? Let's focus so we can learn. So, yeah, a variable essentially is a way to give meaning to a particular portion of memory that contains some data. Give it a label, give it a name, or a label. That is essentially what a variable is. Okay. R functions. We talked about R functions just briefly. We showed ourselves how some functions do a few things in R. We spoke extensively about the working directory, and if you remember, there was something I said about the working directory. I said it is advisable and important for each R project to have its own unique working directory. Why? Does anybody remember maybe one reason why it's important, or even one that I didn't mention? Something that sounds that's reasonably should be a good reason. For easy location, yes. Accessibility, yes. Organization, yes. Organization of your work. Okay. Now the workspace. What did I say about the workspace? I know you probably won't remember this, so that's why the recaps are always good. When you now recap it now sticks. A workspace, I said, is like a tabletop. It's like your desk. Okay. And if you remember, I showed you how with a function you can list the objects you have created in your workspace. Like your variables, which are objects, of course. You created some variables, right? There's where they are. There's where they are. There's a location where they are in your R session, and that place is called the workspace. You can now access those objects. You can work with them. You can delete them. You can create new ones. You can modify them, and so many things. So that is your workspace. And then I spoke about ls function for listing the contents of the workspace. I spoke about rm, which helps you to remove something that is in the workspace. Right? Now R scripts. What are R scripts? What are R scripts? Ernest, what's an R script? You were not here when I was talking about it, but that was okay. Did you come at all? Okay, you didn't come at all. Okay, it's true. I was saying how much I missed you that day. Okay. All right. R scripts, Ernest, you were not here. The video is available. I will send you the email, the links later. R scripts are just text files. They're just text files upon which you have written R commands. What you would write in the R console to give you a result. That day we were not here, so that day we were doing things like 1 plus 1. We were creating variables called X, showing how to create it with some values. So you can do all of this and write them down in a text file, and then save it on your hard disk, or share it with someone else, with a colleague. And those your commands you've written are now recorded. It is a record of R commands that can be shared, can be stored. So that is what an R script is. Anybody can use it. And that is the beauty. That this is really the beauty of R. This is really the beauty of it, because it makes your work reproducible. You can reproduce your work. Someone else can test your scripts and reproduce what you have done on another computer. Okay, and this is what makes R scripting superior to using point and click software. Because when you use, the other day I was with a colleague in the office, and he was demonstrating something, that he was doing with a software, a map, how to know where something is located on a map, right? A station, and all that, with all the legend and everything, and they're getting the data from the map, which also could be done in R. So what he was doing is, I said, this is very nice, but the problem with what you're doing is that all the steps you've taken to produce this map, I cannot, even you that did it cannot reproduce it. You can never reproduce it. Or when you're doing like data cleaning, you pick data, like I was telling you about the work I did here. I found some files. I took the data, I cleaned up the data. There were some errors in the way the data were entered, funny stuff, and we tried to fix it and make it, proper and fit. But the good thing about what we did here is that the original file that was a mess is still there. And all the steps that we took to fix those data are written in a script. It's written down, documented in a script. So, if God forbid, maybe for some reason you lose the data, the newly refurbished database, you lose it. Those original files are still there. You can just, with a click of the button, you run that script, it will bring back the thing for you again. So that is the power of scripting. And then, if maybe we're looking at the database, I said, oh boy, like it happened before several times actually. I said, this thing I did here wasn't actually quite correct. It wasn't really correct. This column is not correct. I need to change this column. All I need to do is to go back to my script and adjust my script a little bit. Just tweak it a little bit to fix that problem. You get me? So that's really the power behind scripting. If I done with a mouse and this is software, all this BB software, I write my click, and then there's a mistake somewhere. I cannot trace it. I cannot retrace my steps to where the problem was created. So there's the work I remember writing those things I wrote here, almost like sleepless nights. I was writing those things. It took me, it cost me a lot of pain to write those scripts. But having done it, I'm cruising now. So you do the work once when you're writing, when you're programming, you do the work just once. The rest of it is just small adjustments. You tweak it here, tweak it there, just improve it, add some features to it. You're just cruising. And when you're going the other route, you are working and working. That's why if you find people, they are working and they're doing the same work round the clock, year in, year out. They're doing the same work because there's no way to improve or build on what you've done in the past. Okay, so this digression now is not part of our talk, but it's just I want you to appreciate why what we're doing is important. And this is how people out there grow, because they have these systems that help them to, keep track of what they're doing and create room for growth. As Newton made a statement, he said, I have not become what I am on my own. He said, I have stood on the shoulders of giants to see further than what they saw. So there must be a way of documenting the work you're doing. Even in your office, there must be a way of documenting your things so that you can always be building and and be creating better systems for your office. Okay? Then finally, we talked about help, how to find help. Okay? That one is normal. Okay, now vectors defined. We're now entering into what we call data structures. This is really the core of R. To be useful, data has to be organized and properly structured. That's why we have data structures. Okay. Did I write anything about this? Let me see this slide. Did I write? Okay. Anyway, pardon me. I made some issues here. I'm seeing some issues here. Okay, but you see, in computers, like I said the other day, computers only know ones and zeros, 1 and 0, 1 and 0. That's all they understand. But with data structures, we can organize our data, and there are rules and behavior that govern the data structures, and it makes computing much easier. In R, we have a number of data structures that we use. We have atomic vectors, we have lists, we have matrices, data frames, and arrays. By the time we finish this short course, we would have gone through all of them. Today we're going to be talking about vectors. Now there are two kinds of vectors. We have atomic vectors and lists. So these two, they are both vectors. Okay. Is anybody here with a math background, apart from Uche? Uche, you did computer stuff. In math, we used to have in math, in linear algebra, we have what we call vectors, where you have like numbers that they are lined up. Okay, so just think of vectors as a chain. Okay, just think of it as a chain. Vectors are essentially unidimensional data structures, so they go in one direction, like a line, a chain, a rope. Just think of it that way. A train that has coaches. Okay? What did I do here? Let me fix this slide. I want to reveal to you source code. This is how this slide looks like. I'm just teasing you. I don't know why why it didn't run that well. No wahala. Anyhow. Okay, that's fixed itself. So length of vectors is either it can't be less than 1. So we can have a vector that is just of length 1. The maximum length of a vector depends on the machine. Okay? This thing we have here, machine, is actually, are you seeing my cursor here? Yeah. Anyways, that pointer, is it working? The pointer, is it working now? Machine. If you type this thing here now in your R console, you will see something coming out. Have you done that? Just type machine, dot machine. The way it's spelled spell it correctly, you'll see something. So this gives you the limits of some of these things. So the largest vector, the size of the largest vector is there among those things. So it depends on the machine. Okay. Okay, let me show you now. Let me show you. Don't worry. Let me show you. Let me show you. This is the console here, my own console. Just look for this console here. Have you seen console? Are you in RStudio?
No.
You're in RGUI.
No,
That's RGUI, now the one we used last time. It's still okay. Yeah, you can still use it. Type dot machine, capital M. Yeah, dot machine. You see something coming out. That is okay. Now look at this cursor here. Integer max, size of long, size of pointer. These are all limits. Okay, they are limits. All right. Atomic vectors. This is the bedrock of our data structures. Vectors are the foundation. Is that clear? I mean atomic vectors. They are the foundation of all our data structures. So if you have like a variable that has just one, the number one in it, that is a vector. All the things that we created last time that I showed you, they're all vectors. Those things that we call variables. Is it working? Right. Okay. Please teach me again. This one is the point, right? This one up here.
it's already pointed. That's easy. It's good.
Yeah, but to point to show the light, the
Yes,
which one do you where you press the point? No, you are scrolling it. I don't want to scroll it.
point. Point at the
Yeah, it's supposed to,
The point is not. The battery is comparison. The batteries.
the battery is weak. Okay. All right, cool. No problem. There's no problem. No problem. So in computing, all data is in bits and from bits to bytes. A bit is a 1 and 0, off and on thing. Okay? And a byte is a collection of bits. Usually it's about 8 or 9 bits. Okay? The byte is in memory is what is called the addressable portion of memory. So there are addresses in memory. So each portion that has an address is called a byte. And usually it's 8 bits. 8 bits make 1 byte. Now this is made meaningful to humans in the form of types. So the ones and zeros that are happening within the processor in the computer, they are translated into types through certain mechanisms, which I will not, of course, not talk about here. I just felt I should highlight it because we're going to talk about types. So there are types of data which make meaning to a human being. It makes no meaning to the computer. All the computer knows is ones and zeros. Now they are atomic because all the elements of atomic vectors must be of a particular data type. They must be of a particular type within any given atomic vector. Now the types can be built in. Types can be built in or user defined. All right, but it's more a slight correction here is that for atomic vectors, we're dealing with built-in types, not user-defined. And when I say user-defined, you, the user of R, can create your own types that make meaning to you. For example, student. You can create a type called student. That student has certain properties. He has a name, a gender, and age, for example. So you cannot create a type called student. Assuming now 3 of you are students here. I can say, okay, I want to create a type of student, maybe to create maybe a data base on this class. And I say object 1 is Ernest, object 2 is Maureen, object 3 is Uche. And all of you have names, gender, and age. Those are your properties. You get? So I cannot create a type called student with that, using your age, using your gender, using your name. Alright? So that's what we call user-defined types, which we will not talk about at all right now. Down the line, we will talk about it. Okay? Now, in lay language, a type, in quotes, which is a built-in type, mind you, would be numbers, words, etc., those kind of things. So these are things that make meaning to a human being from the data that is inside the computer. You see a number, you see a word, you saw A, B, C, D, E, right? Other things are there. You saw a picture, you heard an audio file. These are things that make meaning to you. Now the built-in types for R are numbers, words, stuff like that. Okay? Now atomic vectors are made up of built-in data types, like I said before. Now we have 6 kinds of atomic vectors. 1 is character vector. 2 is integer vector. 3 is double or numeric vector. And 4 is logical vector. Okay? Any question? No question. I thought you asked me why I didn't list 6 here. Huh? You're afraid to ask me. You're afraid to ask me why.
I thought maybe it would be.
It's not a mistake. It's not a mistake.
It's
It's not meant for this class. Even me, I don't use them. There are 2 others, but they're not important for us to mention now. Character vectors. The other 2 are called raw and complex. Raw vectors they're essentially bytes. You can have vectors that have bytes in them, just bytes. You hardly ever need to use them unless you are programming at very low level. Okay, I think I've only had course using like twice or so since I've ever started using R. I was looking at the binary format of a file. I was trying to identify the file by its binary format, by its header. So I used raw vectors to extract that one. Okay. Then we have complex vectors. Complex are complex numbers. That is high level math. It's not our ordinary arithmetic. Okay. Even me, I don't know that one yet, but I've decided that I must study it and find out what is there. Okay. Strings. In computing, we have this term called strings. Another small digression. I'm trying to really explain things to you. Bits and bytes. Okay, bits and bytes. I said. Now, in computing, we have what we call we have what we call encoding. Encoding for characters. If you remember, maybe when you were in school back in the day, when in primary school, they used to teach us then how you code. They call it quantitative, quantitative reasoning, something like that. they will say if one is A and 2 is B, what is C? C will be 3. Do you get me? That kind of thing. So that is what encoding is, and that's how the computer presents characters to us. Okay. The bits is converted to a number, and the number is converted to a character. Are you following me? Now, why we now call them strings? Strings is when you join more than one character together with another one. When you join them together, it becomes strings, like a necklace. So characters are joined together. It becomes a word. As we know in language, it's called a word, but in computing, it's called a string. And why it's called a string is because characters is not only letters that are characters in computing. Even the space that you left between two words, that space is a character in computing. So that's why they opted to use the word strings rather than saying words. So when you put a full stop, that full stop is a character in computing. It has a value that is in bits and bytes. So that's why we use strings. So when you see strings are placed in quotation marks when coding. So when you want to write a string in R, and most of, at least the little ones that I know, the few languages that I know, they always use quotation marks to surround it to show that this is a string. It's a string of characters. So that word there, boy, has 3 characters. The next one, NARC, has 4 characters. That R is easy to learn. I won't count the characters, but note that the spaces between the words there are all characters. So the string is, it begins where you open the quote, and it ends where you close the quote. Is that clear? So we can create an empty vector. So a character vector is made up of strings, one or more strings. Like I told you, a vector must have at least one element. So you can have a string, so you can have a character vector that has a length of 10. You can also create empty vectors. It will be a vector of a type, but it will be empty. But it has that type. There are times when you have to when you have to do certain things like that. So, by the way, as I'm talking, not to stop you from typing this in on your own and trying it out. Like that third bullet, you can type that in your console and see what happens. You know, so that when you now make an error, you can now draw my attention. Then we'll learn something from your error. Okay. Now the limits approximately 2 to the power 31 characters, about 2 billion characters. That's the limit for any given character vector on your computer. At least for my own, I don't know about your own, because it varies from machine to machine, like I told you. But this is what my own machine will give me. This can you can put the whole Bible into one character vector. Yes, you can put the whole Bible into one character vector comfortably. Some character vectors are inbuilt. They are inbuilt, okay? Like if you type letters, with that lowercase version, if you type this one, it will give you something. They are already there in R. You don't need to create them, and they're very useful when programming. So you can see the example code there. I typed letters. It gave me the letters A to Z. And then month.abb, it gives us the names of 12 months, 12 calendar months. gives it to us as abbreviations. Okay? Integer vectors. These are numbers. They are numbers, but they are not strictly known as numerical, entities. To create an integer vector, if you just type 1L, 1 with a capital L, 2L, 3L, 100L, whatever, it will give you an integer vector. And there's a reason why we have the L there. The L, it is with the L that you will set a number to become an integer. Okay, it's not part of the. If you run it on your own, you will see that. If you just type 1L, it will give you 1. You get me? Numeric or double vectors. These are real numbers. Real numbers, and I'm saying this in the mathematical sense. When you say real numbers, we're talking about numbers that are continuous within a scale. 1.1, 1.00000. Those are real numbers. Okay? And then the reason why we say double is simply because it has to do with the level of accuracy of estimation. The number of decimal points it can carry and retain its accuracy. This is more of a historical artifact, because before they used to have what they call singles, numbers that have a smaller degree of accuracy, as in a limit to how many decimal points that number can have, and then still remain accurate. Okay, it has to do with that byte thing I mentioned to you. Okay, and also the limits of the computational powers of a given computer. We have some vectors, some numeric vectors that are inbuilt, that are constants, like pi. We know pi from mathematics. If you type pi in your console, to give you 3.141593. Okay. Logical vectors. These ones are just true or false. Okay. So true. Note that this is code. It's not just English. This is code. This is code. In R, it must be all uppercase for it to be. If you write true in lowercase, now if you write it down in your console, it will give you an error. So it tells something like object true not found or something like that. But if you type it with uppercase, it will give you true, because it works. Okay, right. You can use T or F, capital T or capital F, as true or false. If you type capital T now, it will give you true. Okay, good. Now, 0 is false, or rather, the other way around should be. I didn't say it correctly. I said false is 0. Okay, false is 0. And any non-zero evaluates to true. Okay, so whether -1 or +1, it will give you true. And we have this function there for testing logicals, for testing the logical vectors. We say as logical. You can say that the first one is true, the second one is also true, even though it's negative, but the one that is 0 is now false. Okay, logical vectors are very useful, very, very useful for testing conditions. For testing conditions. Is this true? Is this equal to that? Say true. Is this one equal to that? It's false. Are you getting me? So they're very useful vectors. Now these are the operators for logical, computations, for logic. We call them Boolean operators. Boolean, B-O-O-L-E-A-N, Booleans. Okay? This is the description on the left column. The right column is the keystroke. So when you see something like this, you see, when you say something is equal to this, the keystroke is double, equal sign twice, which means exactly equals. Remember that we used the equal sign before. What the equal sign does is to assign a value. It is not for equality in computing. And in most computer languages, it is the same thing, two equal signs. In some languages, it's even three. JavaScript has three. It has one that is three equal signs. Okay, I will not explain what that one means here. Not equals. You have an exclamation mark followed by an equal sign. That is not equals. Then less than. I'm sure we know this one. Now, this one is from elementary maths. Is there. Greater than is the other one. Less than or equals to. You combine that less than with equal sign. And greater than or equals to. So these are what we use in comparing, in testing conditions and doing certain things. By the time we do some other things, some other operations, you see how useful that these things are. How to make a vector. Like I said, what we made last time were vectors. So by assignment, you can make a vector by assignment. You can provide inputs directly and create a vector. This is usually best for vectors of length 1. It's easiest. Okay? But you can still create vectors, that are longer than 1. You can, right? Another way is by function calls. For example, we have the concatenate function. I didn't do this slide. That thing should have come to the second line. Concatenate means to chain. Concatenate means to chain. It comes from Latin concatenatus, which means a chain. So when you see that C, it means we are creating a chain. Remember, I was saying that vectors are like a chain. This function, anything that you put into this function, it will just combine them and create a vector. It is indispensable in creating a vector. That this C is one of the most used functions in R. Now also, vectors are created as a return value from function calls. Many functions that we use return what they return as the output. They are all vectors. Most of them. Okay, not all, but most of them. Now there are some useful functions that you can use to also that do certain things that are very unique. In making vector. Like we have REP. It's called rep. This one, it will repeat anything you put in this function. It will repeat it. Like if you want to create a vector of the letter A, 10 million A's in a string like that, it will create it for you. You just supply the letter, supply the number of times you want to create it. Right, and it will do it for you in less than a second. Sequence, SEQ. If you want to create a sequence from this to that, from 1 to 10, from 1 to 1 million, to do it for you. Okay? You just give it the first one you want and the second one you want. Start and stop. And then you say how many you want. So if you have a list of, yes, go on.
It's a rep is for alphabets.
For anything, for numbers, for alphabets, anything you put there, it will repeat it for you. Okay? You can grow a vector from nothing. You can create You can create in R we have what we call no. It's not a value, but it's an object. So we have the null object in R. So you can take a name, just like when you are creating a variable. You say you can assign null to x. So x is null. You can just try it out there. Assign null to x. You see that x, if you type x becomes null. Nothing is there. You can use that null to now create a vector. You can now grow a vector to any length. But like I remarked here, it's very expensive in terms of computational time. So it's not usually done. Okay? They just know that it can be done. Now we have an exercise that you quickly do. Can you see this is not too clear, but it's not too large, but I think it's clear enough. Here we have two vectors. One is called x and one is called y. Are you seeing it? Now, what type of vectors are x and y? From what we just discussed. Pardon? Sorry?
Is it numerical?
Numerical. Numeric, not numerical. Numeric. That's correct. It's numeric. Why do you say it's numeric? Yeah, the numbers, yes. But there's something else that makes them numeric. Remember, we have another one that is also numbers. Integer. Integers are also numbers. But this one is numeric. There's a reason why it's numeric and not integer. No. Quoting is only for strings. Quoting is only for strings. If I quote this one now, you can quote this, but they become characters. Let me show you something. Remember this thing that I will show you. I'm sorry. Okay, I'll go back still. And now what for you? Look at this, that first bullet. Can you see the last string there? The last character vector there. What's it? It's 9. It's 9. But it's not, this one is not a number. It's a number to me and you, yes. But we have made it a character. Yes, because of the quotation mark. Are you following me? And it makes sense. For example, if you remember, think back when you're using your Excel, you want to enter numbers, phone numbers. What happens? What happens when you want to enter phone numbers? Takes off what? The first zero. Do you know why? Do you know why? Yeah, because in a number you can't have a leading zero. You cannot have a leading zero and in a real number. It's either 0 or it's 1 or 2 or 3. You can't 0, 1 is not a number. But 0, 1 exists. You can have it as an ID. You can have it as a phone number. 08. That's 080. That number is not a number. If you remember. What do they call it? They call it SSID. It's not. It's an ID. It's not a number. It's an ID. So, but if you're entering that thing in Excel, if you change that column or that cell, there's a place where you can fix the type of content. If you put it as text, that 0 will remain there because it has now become a string. It's no more a number. Are you following now? So that's why this thing, you should know this is important. The fact that it looks like a number doesn't mean it's a number. So your phone numbers are not numbers. They are IDs. They are texts. And that's why Excel will never accept that leading zero. Are you getting it? Okay. So back to the exercise. This one. Talk to me, guys. Talk to me. Uche was saying something. Okay. I said why. He said that they are numeric. I said it's correct.
Okay, because they don't have
No. That is true, but that's not why. I said why are they not integers, for instance? Because integers are also numbers.
it's no leading.
Pardon?
It's no error.
Yeah, but if you remember, when you put in L as when you added L to your input, the output didn't come with L because it doesn't have L. You get me? So this is basically an internal representation of our vector. It's not this is not input. This is output we're showing here. So it's not correct what you're saying. Should I link it to you? It's very simple. That's decimal point. It's a real number. That's why it's called a numeric or double, because it has 2.6, 3 points. An integer will never have point something. It will only be a whole number. 1, 2, 3, counting. Do you know what I mean? That's a whole number. Like that, you get one man, one girl, one boy. You can't have half a girl, right? But you can have half a lemon, half an orange. So those ones are real numbers. But for entities, it's 1, 2, 3. Counting is 1, 2, 3. So that's what are integers. So this is a numeric vector. The two of them are. Okay? Good. Now create these vectors. Create them. Create them now. Fast. Hurry up.
Don't understand, sir.
What don't you understand?
How to create the X.
Yeah, because you went here last week. Okay? So I will just give you one small expo. And it will help them too. When we say create something, this is where I am, okay? This is my console. Let's say I want to create a variable called f. I will put an arrow sign here, less than with dash, and I want to say let it be 8. Okay? When I run f now, f will say f is 8. Okay? So I've given 8 a name called f. Or conversely, I've given f a value called 8. You can look at it either way. And anywhere I carry this f to now, f will be 8. If I say g, let g be 10. If I run g, g is 10. Anywhere I carry g to now, g will be 10. Okay? If I now say f plus g, f is 8 and g is 10. So it should give me 18 if my R hasn't gone crazy. And it's 18. This is what we did last week. Okay? Alright? Now, to create a vector, I told you just now, I said you can create a vector, you can create that, because as you can see now from this picture, this is a chain of numbers. X is a chain of numbers, and in fact they're the same numbers. Okay, but they're different memory, they're different pieces of memory, but they have the same content. Are you getting me? One is X and one is Y. I said you can create them. You can there's a function called C. I will create a chain for you. Okay?
Okay, C is for chain, to create a chain.
Yes. You can use that function called C to create a chain. So I'm going to go back to this thing. How to make a vector. This one here. This function called C. This function is what you're going to use to make your vector. So go ahead and try it. Try it and fail. You start with X first. If X fails you, you let me know. I deliberately didn't show you an example. It's deliberate. I want you to scratch your brains more. Remember I told you, hey, watch it. Last week I told you something. I said there's a way you can find help. Remember I told you. Do you remember? You weren't here. How do you find help for any function? Maureen, tell me. Can't remember. Uche, do you remember how you can find help for any function? For any function at all. Find to open the help page. Help plus start will give you the overall manual, R manual, all those, the home page. But I showed you a function that you can use to get the help for a particular function. That's what you can do. Very easy. You type question mark and then put that function after the question mark and hit it enter to open a help page for you. So like now, what I expect you to do, because I've not taught you about C, I want you to open the documents. Open the help page for C. Have you opened it? Just type question mark and type C after it to open the help page for you. Let me do it. Question mark C. Have you seen it? This one is now. Let me open it here. This is the help page. Combine values into a vector or list. Alright? So look at it here. Usage. Arguments. Objects to be concatenated. Then the easiest place to go to is the examples. Examples. I see an example here. Can you see an example here?
Yes, sir.
This is one example. This is another example. Okay? See this one here? This one here will give you a vector that has 2 and 2. I see it. A vector of length 2 that has 2 as the first element and 2 as the second element. That's what this one will give you. So I've given you the expo. So now do the exercise. Create these 2 vectors with what you know already, or what you now know. And do it quickly. That means don't be afraid to fail. Don't waste time and say you want to read the encyclopedia first before you do it. Try something first and fail it first. You see, one of the beauties about computing that I've learned, it makes you not to be afraid of failing again. You learn by failing. So what you're going to do is that you're going to take that function C. You're going to put in those numbers into the function and run it. Separated by commas. Just like you saw in the example. You can always consult that example. You see them there. See, you are now programmers. Or did you ever dream that you actually be a programmer in your life? Even Uche that is a programmer left it. He dropped it. Nigeria can kill dreams. Hmm? Yeah, good. Which one? Space is good. You use capital C?
Yes.
It's small c. It's a small c, not capital C. Now one trick. Quickly, stop. When you type something in the R console and you want to fix it, you don't need to start typing it afresh. Just do this. The up key, this arrow key, up arrow. If you click it, it will just bring you the last commands you did. You don't need to start typing it afresh. And then now, to fix that thing, just go to the beginning. Use the left arrow key and go down and then fix it. Okay? Continue. You got it. You have made the listen. Eh? Okay, type X.
Maybe because I gave X to consist.
So you see that's your vector you created. It doesn't have a name. So you just give it the output
Of what I had before.
No. The one you did first.
Yes, then X.
It get, no, not the not the X. The one you combined. It gave you a result. The list, the vector with all the numbers in it. But it has no home. It has no address. It has no name. So that is just it's only output, and that's it. And that it doesn't exist in your session. So what you need to do is to assign it to X. What X contains now is the one you gave it before. So now assign what you had before. Do the up arrow key again. Go to the beginning of that line and put X arrow. That will now change the value of X. Give it its new name. Give its new value. Sorry, give X the new value that you have. No, don't press it too many times. Press only once because it was the immediate pass command you ran, or the second one. Okay, it was the second. It was the penultimate one. So go to just do it twice. No, don't type it again. Don't waste time. We are lazy. Programmers are lazy. We don't like wasting our time. Yeah. So go down. Go down to do this. Go down to the end. So put your X arrow at the top.
At the beginning.
Yeah, at the beginning. Put X.
Before the C.
Yeah, at the very beginning of the line.
Just X or
Yes.
you are pushing it to it.
Just put X, put a space, then put the arrow. Just continue. To push that.
Normal arrow.
Yeah. To push the rest of the thing down as you're typing it. You enter it. Which are you alive? Okay. Arrow again. You see? That means it has worked. So now type X. Congratulations. You have made your first vector.
Oh my God.
You have made your first R vector.
Let me do R. Y.
Do Y. Y easy now. Just do up arrow key and change that X to Y. Finish. That's all. You need to type anything because they have the same value. It's the same content. See them. The same content. Just the same thing. Okay, so what is your problem, Ernest? Let me see. Yeah, see what you should do. Up arrow key. What was the last thing? Wait. Now, first of all, you don't need to have a comma at the last number. You don't need the comma there. Okay, that's number one issue. Secondly, this vector, if you run this one now, it will work. But that wasn't the assignment. Run it to work. See, it has worked. But what we want is those things, there are 5. So put all 5 there. Separate them by commas. Put all 5 there, and then assign it to X.
Okay. How will I make X to be at the top?
No, it's not X. X will not be at the top. This is just a picture to represent. I said make a vector that has X. It won't look exactly like this. No, not at all. Are you getting me? Okay. Uche, let me come and check something. Where is that? Like, look at it. Why are you using FG? It's going nuclear, yeah.
Let's come and join you.
What you're doing is very correct. Very correct. Correct. No problem. You see, the good thing about this is that there are so many, when programming, there are many approaches to it. What Uche did, although it's a long road, was he created A, B, C, D, E. Uche, he created A, B, C, D, E. Are you following, Maureen? He puts 2.6 in A, puts 3.2 in B, puts 3.8 in C, puts 4.4 in D, and put 5 in E. Then he used that concatenate function C and put A, B, C, D, E inside it.
But that is long, bro.
It's too long. We don't like such code. It's too long. We like the simpler way.
I tried doing numbers. Then what I wanted to do for Y is not telling me as if it's already been used somewhere. It's not telling me not yet as one. I have to now separate it.
Why it said object undefined is because you weren't assigned to Y. You were using that Y. Why wasn't there before? Ernest, how far? Yes, you are in order. You're in order. See this thing you're doing here now. See, look at this. See this thing you're doing here now. When you type enter, where is your enter? HP. See, this is a vector. 1, but this is 4. You add 1. 4.4, 3.8. He's not typing those numbers. 2.6, 3.2, 3.8, 4.4, then 5. Yeah? Now, and then enter. See, so you see, it's now complete, okay? But you need to create X. So what you use now, you take this thing you have written, this photo you have done here. Go to the top. So type X now, space, less than, dash, space. So this is now, you are now sending this into X. Now enter it. Now type X only. So it does not give you the same thing. Have you seen it now? So now to now create Y, you just do this. Just change, just convert this X you have here to Y. Yeah, that's all. Because they have the same value. Okay? Great. Okay. Now type X plus Y. Type X plus Y. And tell me what you observe.
5.2, 6.4.
Yeah. What do you observe?
He added all the number.
How did you add them? Yes, element by element. Because they have the same length. Yeah? Because they have the same length. You add them element by element, okay? Good. Now, vector behavior. We have what we call coercion. I'd rather you don't use your phones when I'm teaching. 1 is rude. 2, you're missing. You have something very important. Just take an excuse, go deal with it and come back. It's better. You understand? Okay. Vectors will always attempt to force you to have one type only. Okay? Sometimes, for example, if you look at this very carefully, this exercise we just did now. When you typed out this thing in your console, what happened to the 5? It became 5.0. That is called coercion. When you say 5 alone is more like an integer. Do you get me? Okay? Even if you have put 5L, it won't give you an error. It will take it, but it will change it to a numeric element. Because they must be of one type. You get me? The whole vector must be of one type. That's why it's called atomic vector. So that's what we call coercion. You're welcome, no problem. That's what we call coercion. Coerce means to, in English it means to persuade somebody with a certain element of force. You compel them to do something. That is coercion. So R will compel you to have only one type. Okay? And where it's not possible to coerce, it will give you an error. It's not always possible to coerce. And where it's not possible to coerce, it will give you an error. Okay? That's why, if I do this, watch me now. If I do something like this now, if I say, I want to do a vector, like make a vector. I won't assign it to anything. Just input output. Okay. If I say boy, and I say 9. We know that boy is a string, 9 is a number. Okay, and this 9 as I'm typing it, I didn't put it in quotation marks, so it's still a number. Now I want to create a vector with this. If I just type this, what happens? The 9 has been changed from a number to to a character 9, no longer a number 9. So this is what we call coercion. It's coercion in action. Okay? So this is very important. In a practical sense, at times when you're working with data, you see that you are expecting maybe a column of a table to be numbers, and you go and everything is text. Why? Because somewhere down the line somebody wrote something like, instead of, maybe if you write, okay, now let me just give you an example now. 9, 4, 6, 3, 2, and then I now type something like this. No, not this. I'll do something like, by mistake, just by an error of and you put this in, like now in Excel, and you import the thing to R. It will give you this thing in characters. It won't give it to you it will do it appear as numbers. And of course, if I run this thing here now, it will even give me an error, because your vector must have the same type. Everything there must have the same type. Okay. So coercion. We have what we call precedence for coercion. I'll not go into it. Precedence means where it's possible it will be converted. Like now, if you join a number with a character vector, it will convert the number to character, and not the character to a number. Are you getting me? So even if it's like this now, if I say C9, 9, and I say 9. 9 is a character. The first one is a character. The second one is a number. If I enter it, it will coerce both to character. It will not coerce the character own to a number. So it won't. Nothing will happen. It is same thing, same results. So that's what we call precedence. It's a rule of the language. It's a rule of the language that if this happens, they must become character. They must become, no, of course they must become the same, but it's the choice of which one should it become. That's the order of precedence. So character is of a higher precedence than the number. Are you getting me? That's what we mean by precedence. Okay? No, it's a rule of the language. It's a rule of the language. The only way to overcome it is to fix the code. Do you get me? Because every language has its rules that govern it. Recycling. Now, when computer vectors they are recycled, I don't waste time doing it. But later you go and try it on your own, or maybe later. Just remind me later. We'll just do it. Recycling. For example, now when you added x and y, it added 1 upon 1 upon 1 like that, because they have the same length. If one of those vectors is shorter than the other, right, the result will be different. It won't fail, but recycling. What happened? Okay, like now, if we have a vector of 5, of length 5, of course, it brings me to this other point. It's called vectorization. I said duh, because of course it's vectors. Now, what do we call vectorization? And this is one thing that makes R powerful, very powerful. A vector can be length 1 to anything, millions and even billions. Okay. If I want to add 1, or add a number, or run a function on a vector, it will run through the whole vector, and to run through the whole vector, that operation will happen down the whole vector. Okay. Look at this now. Z. Let me say this is 1 to 9. Okay. Remember I was saying that 1 to 9. That's colon is a range. And in Excel, is the same thing, right? So if I say Z is 1 to 9. Can you see it? 1 to 9. Now, if I want to subtract 1 from, I can subtract 1 from this vector. If I say Z minus 1, the rule that we call vectorization is that it's not going to add 1 at the end of Z. It's going to remove 1. Sorry, it's not going to remove 1 from Z. It's going to remove 1 from each element of Z. So what you have is 0 to 8. This is what we call vectorization. And it's so you can have, and this is why R is powerful for data management, because you can have millions of records, millions and billions of records, and you want to just move 1 from all, just minus 1. It will go down and move 1 from all of them. You get me? And this brings me to the point of recycling. Now this is because it's 1. But if it's maybe 2, right?
I thought if you are specifying the kind of number you are removing, like 9, this 1 to 8, 1 to remove 1 to 4.
You can do it. And but I will not go into that right now. But I'll mention it to you. As we go down, we'll get there. It can be done. Now if I say minus, let me just call something minus. And I say 1 and 2. You have not forced me to. The thing I say I'll skip, I'm not forced to do it. That is recycling now. We're not going into recycling. It's the same principle, right? Because this one was only one, a vector of. Because this 1 is a vector of. Okay, it can be called a vector, but it's constant, but it's 1. We moved it from all the elements 1, 1, 1. And if I now say, yes. I want to do it now. I want to do it now. If I say Z minus, Z minus, I have a vector called minus that has 2 elements in it. It gives me a warning, but it has run the thing. See what it says. We have 0, 0, 2, 2, 4, 4, 6, 6, 8. Have you seen something here? This is what we call recycling. And it gave me a warning. Warning, Z minus. Longer object length is not a multiple of shorter object length. Okay? No, it can be, but the warning, a warning is not an error. It's just a notice. Just in case you did it by mistake. But this is what's happening. But just in case it's a mistake, note. That's a warning. But now I did it intentionally to demonstrate recycling. So they are not on the same length. 1. So what R has done is that it has gone. Look at this now. This vector minus is like this. 1, 2. So when I said Z minus, this first element 1. Let me put them side by side so I will see them. This 1 minus 1 is what? 0. 2 minus 2 is what? 0. I will see it here. 0, 0. 3 minus 1 is what? 2. 4 minus 2 is what? 2, 2. Have you seen it? 5 minus 1 is what? 4. 6 minus 4 is what? 6 minus 2, I'm sorry. 4. Okay, 4, 4. So this is recycling. 7 minus 1 is what? 6. 8 minus 2 is what?
6.
6, 6. Now the last one is 1. It's recycling the thing. It goes to the beginning of value, no, recycling it like that. So now here is only 1. Only 1 is left. So it's now 8 minus 1. Sorry, 9 minus 1, which is 8. So this is what we call recycling. Like that's what I was talking about vector behavior. Recycling, okay? So when there's a mismatch in their size, it will recycle the thing. So this may be desirable and it may not be desirable. So at times when you're doing something, and thank God R will give you a warning to alert you. Say, oh boy, this thing is recycling. Oh, is that what you want? You get me? All right. Now vector attributes. R data structures can have metadata known as attributes. So all data structures in R can have attributes, and as we go, we'll be using them very well. Now, one of such is what we call name. So we have what we call name vector. You can give the elements of a vector a name. Look at this code there. We have a vector here that contains 4 elements: top, bottom, left, right, and we call it unnamed. That's the name. So when we print unnamed, it gives us the value: top, bottom, left, right. Okay. Now we want to create a named vector. We say named. We use the same C function, combine, concatenate, and now we give it a name. We say north. North is top, south is bottom, west is left, east is right. We're talking about named vectors now. Hold on, I say hold on, sorry. Named vectors. Now we say named. When you now print named, you see it gives you exactly the same thing, but you now see that north, south, west, and east are there as like labels. All right. There's a reason why this is useful. Okay, there's a reason why it's useful. So when it's possible, or when it is convenient, or when it's relevant, you can actually give the elements of the vector a name, as we have done here. All right. Now the vectors named and unnamed, they are equal, but they are not identical. For obvious reasons. The values are the same, so they're equal. See, look at this code. I put named, and I put that logical operator, double equals, named. And it tells me true, 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 true. So all the elements are true, 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 true. They're all the same. Okay? But when you say identical, there's a function called identical that we use to test objects. Are they the same thing? Are they the same objects? It says false, and the reason why it's false is simple, because one is named, one has names, and the other one doesn't have names, but the values in them are the same. The values. So when you are focusing only on the value of a vector, it's fine. But when you need the names, you have an issue. Now this thing I'm showing you now will become very, very clear to you when we enter into other structures. Because as you know now, just like now, when you have a table, the table is not useful if the column, if you don't have a column name. You know that now. It's not very useful now. If you don't, what is this? You must know what it is now. So the column must have a name. That column name is what you call metadata. It's data about the data. So the same thing here. This is data about the data. Your main data is the actual value, but you're not giving it a label. All right? Like this is a chair. If I drop this chair now on this road, nobody will know that this chair belongs here. If I drop this chair on, that's good. Nobody will know like this chair. And by the time you put it on the back, NARC, Nehemiah Apostolic, I put the address. Huh? You know that chair that doesn't belong to his blood chair belongs to this place. That label is called metadata. While this chair is the substance. Do you get it? All right. So to collect the names of the name vector, like when programming, you can use the function called names to give you back the names. So you want to know what are the names of this vector self, or of this thing. You just put names to give you back the names. So as I said, cardinal points is my. I made a variable called cardinal points, and I put names of named, and you now see the thing down there: north, south, west, east, as a vector now. Are you getting it now? Good. Now indexing. Your question. This is the answer to your question. We use the bracket operator to work with elements of a vector. We can get or set vector elements. I will not go into it, but in the exercise that I have prepared, you will see it all there. So with this, you can now, if a vector has 10 elements, you can use this now to remove one, or you can add one to it, or you can find out, a particular element. You can locate it. Actually, I was supposed to have said more here, but I think I was in a hurry when I was doing this slide. So, but the exercise adequately covers for this. And the exercise I'm giving you is not like this one you are sweating now. You are sweating. It's not like that. Okay, it's just I've done all the scripts. It's just for you to run the scripts down from top to beginning, from top to bottom. And then now see what happens. The outputs. That's the kind of exercise I give. So don't worry, don't fret, don't panic. So lists. Now lists are also vectors. Okay, but they are not atomic vectors. Are you hearing me? Okay. So they are unique data structure in that they can contain any kind of type or data structure as an element. They can contain anything. You can just join anything. You can jumble up anything. Okay, and in a chain like that. Like when we said machine, that thing you saw was a list. Just a list, just a list of things. In fact, this list can contain. You can have lists of lists. You can have a list inside a list. Okay, so they are very beautiful structures. They are very useful. So the use of lists is only limited by your creativity, imagination, or your degree of laziness. Like people like me who are very lazy, I use lists. Shake it. Let me tell you one story. In the office one day, my boss traveled overseas, so one of the directors was handling, was acting in his stead. So usually when they act like that, they run through maybe some files and then send back to him. So I mean, as SA now, I don't know what that one of the directors, she just said, okay, let her send the files to me to summarize after she has finished treating them. Just send me this file like this. I said, how can you give me this? So I said, okay, I'll use R for this thing. Summarize this file, that'll be very easy. So I use R, I use lists. Okay? And I created like a structure for each file. File name, file number, content, so the page treated, what was the summary of the issue, you get? So I created a list for each file and a list for all the lists. That was what I did. And packaged the whole thing. So I was able to roll out the thing. What happened, summary, just use R and roll the thing out. You get? I know what I would have suffered if I done it with Word or something like that. I know how I try, and I won't have that flexibility to use how I want to use it. Okay. To make a list, use the function called list. This function, I'm creating something called vec list. Right? These are our two vectors, which we just did here as exercise. Remember? Okay? I said x is x. Now the x on the left is the name. Right? Even you see, this is the libretto. So you don't be confused. The x on the left is the name. The x on the right is the object, which is the vector. Okay? So we are creating a named list, a list that has where the elements have names. And y name is receiving the value of y object. Let me say this another way, so you understand the principle. In a function in R, usually we can have what we call function parameters. Now, what that means is that a function is supposed to do some work for you, change something for you. That's why it's called a function. Occasionally, and in fact most times, you want to provide an input to a function to now give you an output. Are you getting me? For example, if you say you have a function called add 2 to any number, you can make a function that any number you add to it, it will add 2 to it. That's a function. I call add 2. Add 2. That's all. That's the name of the function. If I put 10 inside function, it will bring out 12 for me. If I put 14 inside it, will bring out 16 for me. That's the function. So you think of the function like, you know what they call a black box. You put something inside, to do the work for you, and give you a result. You don't care how it does it. What you want is your results. That is a function for you. Do you get me? So now in this example I gave you, this hypothetical function I gave you, the add 2. The argument we're giving it is the input. The argument is the input, while the value, the return value, is the output. It's like a blender. Just think of it a blender. You want to make stew. What you want, you don't want raw tomato. You want ground tomato. Is it not? So your input is the raw tomato. You don't know how they made the blender. You don't know how the thing works. What you want is that when you say on, the thing will do the work for you. And that's all. That's a function for you. Somebody somewhere, maybe in Hong Kong, put together the blender. Likewise, somebody somewhere put together a function. Somebody somewhere, I give it to you, say use it. So you put in your argument, gives you the output. So this is what is happening here. The x on the right hand is our input. The x on the left is just that's what is receiving our input. It's like the cup of the blender. Are you getting it? Does this analogy help you to understand this thing? Then when you have finished the whole thing, though, if it's that one that they used to use in the village, the one they do like this now, the input comes from here, the output comes out there. That's the way functions work. So what we want here is we want to create a list. This function called list will give you a list. Anything you put inside it will create a list for you. So, and we want to create a list that has names. We put X. We want to name this one X. If I put A there, it will still be, it will now name it A instead of naming it X. So instead of now being X, by the time we are through, it will now be A and B, which you can try out on your own. Okay. So this is a list. Look at output there. $X. That $sign shows you this is one element of the list. $X. And then this other one says $Y. Okay? So these are the two vectors we had before. Now we have not combined them into a list. So we now have a structure that can accommodate something that we have created, separately. So lists are very useful. With lists we can overcome the type constraints. That's that issue of it must be one type. You can have any type you like with lists. You have no limit to what you can do. So this makes them very useful in creating user-defined types. Like I was telling you now, you want to create an object, a type, and call it student. Which has a name, has an age, has a gender. Now name normally would be a character vector, it's not, because it's a word. And age normally would be a number. Gender would normally be a character. Right? So you cannot combine those three in a normal vector. As an atomic vector, you cannot combine those three. But with this list, you cannot combine them. You can have name. So as you say, you now say list. Name. Name equals Uche. Age equals 70. Gender equals male. Just imagine it the way we did it here. It will not give you a list. Maybe you now said student. His name is Uche. His age is this, and his gender is that. Yes, I'll do it for you practically, so you understand. Student. Lists. And I now said name. Name must be string, right? So I must use quotes. Then I say age, 70. And I say gender. Gender, male. Let me add something else. Let me add a logical. Is fine. False. Which are you fine? So have you seen it now? Name is Uche. Age is 70. Gender is male. And he is fine. False. You get? Are you seeing it now? So this is now student. Okay? I'll stop it here. There's much more that can be done, but this is just the basic.
The other fine.
Which one?
Yeah. How did you type? Is it a capital F that you typed?
Yes. The way I'm seeing it, that's the way I typed it.
False.
I typed false, capital F, yes.
So there was the one we had.
F.
Capital F.
I used false.
Complete.
Yes,
if you had typed
F,
capital F,
it will show false.
come out
It will show false. We're cool, right? Okay, great. So, oh yeah, no, but this is very interesting. Lists are very interesting. You can use it for anything. Okay, but like I said, you must have a foundation. The vectors are the foundation, because So something must be in the list, and it must be vectors. It must be based on vectors. Do you get me? So you must know the vectors. Because no matter how many lists if you list upon, you can have lists that has lists that has lists that has lists. Somewhere there must be a vector inside it. Are you getting me? There must be a vector somewhere at the end of the chain. There must be vector involvement. So this is the exercise. I told you that you need the internet. You have to go there and pick up this thing. This is the URL. Go there and pick up this exercise. Download the R script. Run the script line by line. Each time checking the output. Let's discuss the results. So now, that's what we'll do now before I go. Just download this thing now. See where it's from. This is the URL. https github.com/devsolutionslimited. Yeah, just open the page. Open the page and download it. You can't do it now. You don't have internet now. Sure? There's nobody you can borrow from here. Moi, do you have internet? Do you have internet? This file is less than. This file is not up to. This file. No, you see, sorry. That's Windows for you. So you need to. This file is not even up to. I'm not sure it's up to 10 kilobytes. So it's a very small file. It's a very small file. So do you want me to leave it for you as an assignment to do on your own? Huh? Okay. When next are we meeting? Friday, right? Same time. Okay. Let me just show you. Let me show you what to expect. I'll open the page for you so you can see what to expect. Am I even online? Not even online, sir. See me here. Let me connect. Okay, I don't have this thing, sir. I just remember though. I don't have a network here, right? MTN. Nehemiah, give me this in now, you guys. Internet now, internet.
What happened to that was not my own is 500, but 1 gig. But when I put it on, it connected straight to one of my laptop and I didn't know. And it's like this man connected to. It was 3 people.
Remind me.
Blocked
there's a way you can set your this thing so anytime you're using the hotspots, do not do updates. You only do it over wireless. What's not found? You're online now. Mine is working stuff. Let me use mine. It means you didn't type in the correct thing. That's probably what it means. But let me test the link here in case I made a mistake. internet.
Those messages that copy to
No internet for me. No internet for me. So this is what you see. Don't worry, I can mail it to you. I can mail it to you. It's not a big deal. I'll mail it to you. Yeah. Oh no, let me just give you mine. So I just email me once. Now that script looks. Let's try this. You have. See the script here, huh? So what you do is just run it line by line. In our studio, you can just click this button to run line by line, okay? There's a button here called run. In our studio, there's a button. See my cursor here? There's a button here called run. If you click here, this is my mouse, right? The cursor is here in the script. If I start from the first line here, line 1, I say run, it goes down, okay, and starts running the script, okay? Now you can see the console, everything is running there, okay? So this is how the thing is just working, all right? So I will not go through it with you. Just try it on your own. Let me just go through and make sure that there are no errors. Yeah, everything is fine. Okay, cool. So it's all fine. The thing is working well. No issues. Right. So I'll mail this to you, as well as the link to the video. Thank you. Any questions? Questions? Any? None. You okay? Pardon?